Welcome back. In the last video, we discussed a few criteria to choose which pre-trained model you should use. And inevitably, this is going to be quite a hard decision to make. However, you can't go through all of them, so we're going to stick with EfficientNet V0 for now. If you think there's a better one, please let me know. I'd love to know. So 3.2 is setting up a pre-trained model. Let's see how we can do it. So we want to create an EfficientNet V0. Want to create an instance of a pre-trained FNet V0. So let's jump into here. If we go into this EfficientNet V0 weights, we can instantiate this model using EfficientNet V0. And so again, this is from the paper. A lot of these pre-trained models are from some sort of research paper, and PyTorch have baked them into the library. So that's just something to keep in mind. That's where these models have come from. And they typically don't make it into the library unless they're a good model. So if you use one from the Torchvision library, you can probably bank on it being at least pretty good. So let's write in this code, or just copy in this, pre-trained EfficientNet V0. I wanted to show you the old way of doing things, old method of creating a pre-trained model. So this is prior to the Torchvision v0.13. I'm showing you the old version because at the time of recording, version 0.13 is very new. It's not even out yet, but you might come across this way of doing things in older PyTorch code, but it is going to start to error over time. So just keep that in mind if you see this out in the wild. So torchvision.models, we can create it by going EfficientNet V0, and of course you could substitute this for any of the models within Torchvision models. And then if we set pre-trained equals true, what happens if we run this? It's going to download some weights. That was that download bar, so it's downloading the pre-trained weights. However, look at this. The parameter pre-trained, so pre-trained equals true, is deprecated since version 0.13. That's why we've been focusing on 0.13. And will be removed in 0.15. Please use weights instead. So that's an error message there. And so new method of creating a pre-trained model is, this is Torchvision v0.13 plus. So I'm going to comment this out. And then we're going to go model equals, or first and foremost, we set up the weights. We don't actually need to reset them up because we've got them above, weights. But I'm just going to do it again for completeness. If we go weight equals torchvision.models EfficientNet V0 weights. And then we're going to go .default, because if we go here, .default equals best available weights. This will depend on what model you're using, of course, right? .default. Default is the best available. And so there's a .default because some models, this is the benefit of using the updated, some models have different versions of their weights. So if a better recipe, such as version 2, comes out, is it got recipe here? Yeah, so now you can see how the weights were obtained. So some of these have V2, look at that, ImageNet B1 V2. So if the new version of the weights get improved, instead of just setting pre-trained equals to true, we can download a different set of weights. So that's the benefit of using this. So a whole bunch of different other model weights here. If you want to use a different model, make sure you're lining up the model that you're using with the weights that you'd like to use. So now let's set up the model in the new way. Torchvision. We've got the weights.models. Now we're going to go EfficientNet B0. Then we're going to set the weights parameter and make sure this is weights, because I went a long time recently of just having this as weight. So weights, make sure it's weights. Weights equals weights. So all we're doing is downloading this weights, pre-trained weights, and putting them into our model. And then if we have a look at our model, let's see what happens. Oh, look how easy that was to create a pre-trained model. Now this is the EfficientNet V0 architecture. Have a look at how many layers are here. Oh my goodness. Keep scrolling up. We've got some convolutional layers here. Conv2D. We've got a Silu activation there, batch norm 2D. All of these are in the PyTorch documentation if you wanted to look up. We keep going. Oh my gosh, still going. This is how many layers. This is the benefit of using transfer learning. We get all of these layers someone has built, so handcrafted these layers for us. And now we get to leverage them for our own problem. Remember when we were building tiny VGG? If we go into here, custom data sets, when we created tiny VGG, these are our layers. So we had how many layers? That's what we had for tiny VGG. That was our previous model we built by hand. Now look at our model. Now I'm going to get you to just concentrate on the 3 big sections here. We've got features, and if we scroll down, all of these layers, this is what happens when we've imported it from Torchvision. This will be a similar process, all of these layers from a lot of the other well-performing models. Keep going. Model, oh, we at the bottom yet? Oh, we're getting close to the bottom. Beautiful. Now, average pool and classifier. All right, so we're going to break this down into 3 main parts. So if we go model.features, these are the feature layers, all of these layers. And then we have model.average pool. We've got an average pool. So that's going to collect all the features and average them. I'll discuss what this means in a second. And then we have, finally, we have a classifier head. So this is what we're going to be altering for, we're going to alter the features and the classifier head for when we want to customize this model to our own problem. So this is the output layer of the final layer of our pre-trained model. And what you'll notice is that it has out features equals 1,000. So that 1,000 comes from our model being pre-trained on ImageNet. So if we go into here, ImageNet 1K, so 1,000 is because ImageNet has 1,000 different classes. So I just want you to think, what do we need to change this value to for our pizza, steak, and sushi problem? If this is trained on ImageNet, and ImageNet has 1,000 classes, how many classes do we have? Pizza, steak, sushi, so 3 classes. So we're going to need to change this to 3 because instead of outputting 1,000 features for 1,000 classes, we want to change it to 3 for 3 classes. I've got a colorful slide that explains this a bit better. Let's code. So the type of model we're going to be building here is an efficient net feature extractor. You may have never heard of feature extractor before, but we're going to discuss what it is. There's another way that these models are referenced is EfficientNet B0 backbone, but this is just a truncated version of what we just saw, the output. So we've got features. This is going to extract features from an image. Now, what is a feature? A feature could be anything that you could imagine. Now, these layers are going to look at our image of pizza, steak, sushi and extract a feature. For example, it could be the fact that pizzas are curved, they're circular shape. It could be the fact that steak is darker color. It could be the fact that sushi is usually small. So this is what's going to happen with this features section of layers. It's going to try and extract, I was thinking of the right word there, extract features from our image. And then this average pool layer is going to convert all of these features into a single feature vector. So it's going to compress everything that this features section has extracted from our image into a single vector. And that vector is going to be of size 1280 because our linear layer here takes 1280 input. So essentially what this whole process is doing is compressing our image into a single vector of 1280. But we'll see this later on. We're going to get hands-on with this. I'm just discussing this out loud. Then the final classifier layer is what turns that feature vector, or the compressed version of our image, with hopefully some learned representations of what's in there. All of these features, by the way, are going to be flavored by what our model has learned on ImageNet. Then we're going to adjust this classifier layer to turn those feature vector, or that feature vector for each image, into an output of prediction probabilities for 3 classes instead of 1,000. So we can adjust this depending on the number of classes we have. So to break it down, we're using an EfficientNet B0 backbone. We have a features section. This is going to extract patterns out of our images. And we don't define what those features are. This features is using patterns learned on ImageNet. So it's going to define those. That's the whole magic of machine learning. This average pool section is going to compress those features into a single vector of size 1280. This is the input and output shapes that we've discussed so much. And then this classifier head is going to further either compress those features, 1280 into 1000, or into 3 for the number of classes that we have. So we've got lots and lots of layers, but that is the power of transfer learning, is we are taking a working computer vision architecture and applying it to our own problem. So this is a feature extractor model. It's called that because we generally keep all of these layers intact. And then all we do is we change the last layer. So there are other types of transfer learning, and we're going to discuss that in the next video. And then we'll get hands-on building these feature extraction models that I've been talking about. I'll see you in the next video.